This is mathheals.com, and you can find more links to math YouTube videos on this site. Let's take a look at derivatives of exponential functions. Let's first write down our formula. If we take the derivative of e to the x, the derivative of e to the x is e to the x. Now instead of an x there, we have something more than that. Like we have 2x minus 1, or x squared minus 3x plus 5, or something. We'll just put a u there to represent anything. Well, the derivative of e to the u is e to the u times the derivative of u. Like that right there. Which is equal to, I'm going to write that in terms of u prime. So u prime e to the u. Now how I'll work all these problems is I'll set them up with this first formula. But oftentimes in books you see it written this way. And these are what we're going to be using in this section. So let's take a look at our first problem. So we've got y is equal to e to the 3x minus 1. And the instructions say find the derivative. Well, the derivative of e to the 3x minus 1 is e to the 3x minus 1. That never changes. But then we have to multiply it times the derivative of the exponent. So we'll multiply it times the derivative of 3x minus 1. So we got e to the 3x minus 1 times the derivative of 3x minus 1 is 3. And we'll put the 3 out in front. So we got 3 e to the 3x minus 1. Second problem. We got y is equal to e to the cube root of x. Well, the derivative of e to the cube root of x is e to the cube root of x. That never changes. But then we have to multiply it times the derivative of the exponent. So multiply it times the derivative of the cube root of x. So that's e to the cube root of x. And it's best to put this in rational exponent form, fractional power form. So this would be x to the 1/3. So we've got e to the cube root of x. The derivative of x to the 1/3. We take our power, put it out in front, lower it by 1. So we've got 1/3 x to the negative 2/3. Well, we got we're going to have a fraction here. So we put the e to the cube root of x up on top. The 3 is down below there. And the x to the negative 2/3. We're going to move that down below, and it'll become x to the positive 2/3. Again, when you take anything opposite of where it's at in a fraction, the sign of the exponent changes. And that's our answer. Take a look at this one. Got y is equal to x squared e to the 9x minus 1. Find derivative. Well, this is the product rule. So this will be our p and this will be our q. P prime would be 2x. Q prime, the derivative of e to the 9x minus 1 is e to the 9x minus 1 times the derivative of the exponent. So multiply times the derivative of 9x minus 1. That gives us e to the 9x minus 1 times 9, which gives us 9e to the 9x minus 1. I'll always show a lot more steps than you need to show on these. Okay, so y prime, p prime was 2x times q, which was e to the 9x minus 1, plus p, which was x squared, times q prime, which was 9e to the 9x minus 1. Now oftentimes they'll factor out what they have in common, and these both have an x, and they both have an e to the 9x minus 1. So factor out an x, e to the 9x minus 1. That's gone, we're left with a 2. This e to the 9x minus 1 is gone, we left this 9, and we took one of these x's away. So that gives us plus 9x. Now sometimes they don't do that. Sometimes they'll leave it in this form, but each book's kind of different in that regard. But anyway, that's our answer. We can grab a drink, and then we'll look at the next problem. Okay. Number 4. We got y is equal to e to the x plus e to the negative 2x to the 5th power divided by 3. Now I can rewrite this one as 1/3 e to the x plus e to the negative 2x to the 5th power. And now the instruction is find the derivative. This is a chain rule. We got parentheses to a power. So with the chain rule, we take our derivative, we put it out in front. What's inside the parentheses remains as is. We lower our power by 1. And then we multiply it times the derivative of what's inside the parentheses, which is e to the x plus e to the negative 2x. So that gives us 5/3 e to the x plus e to the negative 2x to the 4th power times the derivative of e to the x is e to the x. The derivative of e to the negative 2x is e to the negative 2x times the derivative of the exponent. The only time you don't have to think of that is when you just got a single x, like this right here. Because the derivative of x anyway is just 1. So we got 5/3 e to the x plus e to the negative 2x to the 4th power times e to the x. The derivative of negative 2x is negative 2, and I'll go ahead and put that in front. Like that right there. Now, you may be looking at this, and you're thinking, we got a negative exponent. Well, do we have a negative exponent? I don't know. If x is negative 3, for example, then I'd have negative 2 times negative 3, and this would be a positive exponent here, and this one would be a negative. So when you got variables up in the exponent, you don't use the same kind of rules of trying to get rid of negative powers as you did before. Now I could factor out an e to the x here. This has an e to the x, and this, as weird as it seems, I could factor out an e to the x to that. But I'm guessing, probably guessing incorrectly, but this is the form that they'll leave the answer in. Let me save this. This is derivatives of exponential functions. Okay, let's look at our next problem. So we've got y equals e to the 4x minus 2 over e to the 4x plus 5. Well, this is the quotient rule. This will be P and this will be Q. So p prime, the derivative of e to the 4x minus 2 is e to the 4x. The minus 2 drops away. But we have to multiply it times the derivative of the exponent, which is 4x. So the derivative of 4x is 4, so we got 4e to the 4x. Q prime. The derivative of e to the 4x plus 5 is e to the 4x, 5 drops away, times the derivative of the exponent, which gives us 4e to the 4x. Okay, let's plug in everything we got now. P prime is 4e to the 4x times q, which was e to the 4x plus 5, minus p, which was e to the 4x minus 2, times q prime, which was 4e to the 4x, all over q squared, which was e to the 4x plus 5 squared. Now I'm going to double check myself. P prime times q minus p times q prime. Okay. Well, up on top, they both have a 4e to the 4x, so I can factor that out. So 4e to the 4x. And that leaves us e to the 4x plus 5 minus, and this is going to flip the sign of everything inside the parentheses, so it becomes a negative e to the 4x plus 2 over this. Well, the e to the 4x minus e to the 4x inside the brackets here cancels. 5 plus 2 is 7, so we got 7 times 4. That gives us 28 e to the 4x over e to the 4x plus 5 to the second power. And that's our answer. Slope of the tangent line. Probably. Yeah, I have room there. Okay, we got y equals e to the x over 3. And it says find the slope of the tangent line to the exponential function at the point 0, 1. So find the slope of the tangent line. At a point. Okay. Refresh your memory. Our first step was to find our derivative. Well, the derivative of e to the x over 3 would be e to the x over 3 times the derivative of our exponent. Well, the derivative of x over 3 is just 1/3. And I'll go ahead and put it out in front. So we got 1/3 e to the x over 3. Step 2. Plug in the x part of our point. And change the notation to m. Okay. So instead of y prime, I change it to m. Equals 1/3 e, and the x part of our point. This is x and this is y. So the x part is 0. So we're going to plug 0 in for x. So I got 0 divided by 3. Well, 0 divided by 3 is 0. And e to the 0 power is 1. So then we get the slope of the tangent line at that point is m equals 1/3. Let me save that. Okay, let's look at our next problem. These are nothing a whole lot new, just kind of refreshing your memory, and we're just applying them to a different derivative now. Different technique, I should say. Y is equal to e to the 3x minus 1 at 0 and 1 over e. And find the equation of the tangent line. So find the equation of the tangent line at a point. Our first step is to find our derivative. Well, the derivative of this, the derivative of e to the 3x minus 1 is e to the 3x minus 1 times the derivative of our exponent, chain rule. So we get y prime is equal to the derivative of 3x minus 1 is 3, and I'll put it out in front. So we've got 3e to the 3x minus 1. Now what we're going to do is we're going to change y prime to m and plug in the x part of our point. So y prime becomes m, and we got 3e, and the x part of our point, this is x and this is y, so we'll plug in 0 for the x. So we got 3 times 0 minus 1. So we got m is equal to 3e, 3 times 0 drops away, and we got negative 1, which then gives us m is equal to 3 over e to the first. Remember, you take a negative exponent opposite of where it's at in a fraction. So we got m is equal to 3 over e. Step 3. Into y equals mx plus b. Plug in the given point for x and y, and m from step 2, and solve for b. So into y equals mx plus b, plug in the given point for x and y, and m from step 2, and then solve for b. Well, up here we're given this point, so that's our x, that's our y. So we'll plug in 1 over e for the y. M from step 2 we said was 3 over e, and x is 0. And then solve for b. Well, in this particular case, 3 over e times 0 drops away, and we get b is equal to 1 over e. And don't forget step 4. A lot of people forget this step. Actually, write our answer down. Is asking for the equation of the tangent line, so we need to plug in the m we identified. Now m in step 2 was 3 over e, and b in step 3 was 1 over e. So we plug both of those in, and that's our answer. Gonna need more room than that. Let me save that. And let's look at this problem. We got e to the 3xy plus 7x to the third minus 2y is equal to 5. Now we can't easily solve for y, if maybe not even difficultly maybe we can't even. So that's where implicit differentiation is especially handy. You can just take the derivative of everything where it's sitting. So we'll take the derivative with respect to x of e to the 3xy. We'll take the derivative with respect to x of 7x to the third. We'll take the derivative with respect to x of negative 2y. And we'll take the derivative with respect to x of 5. Okay, so for our first one here, the derivative of e to the 3xy is e to the 3xy times the derivative of the exponents. Now the derivative of 7x to the third is 21x squared. Take your power, put it out in front, lower it by 1. Now the derivative of negative 2y, we're taking the derivative of this with respect to x, but it's really y. So we're going to take the derivative just like normal. So the derivative of negative 2y is negative 2, but then remember, since it's y, we have to add on a y prime. And derivative of 5 is 0, so that drops away. Okay, so back to here. If you got a number, you can put the number out in front. So I don't want to worry about that. So I'll put it out there. So then we got derivative of xy plus 21x squared minus 2y prime equals 0. Now this is the product rule here. So this is going to be p, and this will be q. P prime will be 1. Q prime, you take the derivative just like normal. So the derivative of y is 1, but since we're taking derivative with respect to x and it's really y, remember we have to add on our y prime. So our product rule, we got p prime q plus p q prime. So we got 3e to the 3xy times, and I'll put this in parentheses, p prime, which is 1, times q, which was y, plus p, which is x, times q prime, which was y prime, plus 21x squared minus 2y prime equals 0. Which gives us 3e to the 3xy times, and that next to parentheses indicates multiplication. 1 times y is y plus x y prime plus 21x squared minus 2y prime equals 0. Now we're solving for y prime. Now when you're solving anything, you get rid of parentheses. So we use distributive property. We're going to take the 3e to the 3xy to the times y and times x y prime. So that gives us 3y e to the 3xy plus 3x y prime e to the 3xy plus 21x squared minus 2y prime equals 0. Now we want to get everything with y prime on one side, everything else on the other side. I guess I might as well just take the y primes to the right side. Like that. So we get 3y e to the 3xy plus 21x squared equals 2y prime minus 3xy prime e to the 3xy. Now probably I should be double checking myself here. P prime q plus p q prime. Not the smartest thing to be making these at midnight. I'm not quite as alert as I am at other times of the day, but I did take a long nap when I came home. Must be like an old man or something. Didn't have to go to bed at 6 o'clock then. Okay, multiply that through. Okay, get that. 3x y prime, got that. Okay, take everything over there. Signs change. Okay, that looks right. Now, there's two ways that we usually did these before. The most common way is we'd combine together like terms. Well, these are like. I wouldn't necessarily call them terms, though. They don't fit that. But we can't really combine them together very easy. The second way to get y prime by itself is to factor it out, which is what we'll do here. So the left side remains as is. On the right side, we'll factor out a y prime. And that gives us 2 minus 3x e to the 3xy. Okay, we're trying to get y prime by itself, so we're going to divide both sides by this 2 minus 3x e to the 3xy. So we've got 3y e to the 3xy plus 21x squared divided by 2 minus 3x e to the 3xy equals y prime 2 minus 3x e to the 3xy over 2 minus 3x e to the 3xy. Those are going to cancel. And we get y prime is equal to 3y e to the 3xy plus 21x squared 2 minus 3x e to the 3xy. So we may make a basic math error somewhere. Just looking around, trying to find a piece of paper. How can I not have any paper? Nothing. Absolutely nothing. Oh, here's something. Some garbage that I can write on. Well, not garbage, but some old letters. Okay. Of course, now I've got any pen. Here's a pen. 3y e to the 3xy plus 21x squared. This is kind of the hardest part, is actually writing it down correctly again. E to the 3xy. Okay. So where we're at now, I'm continuing up here, is we got y prime is equal to 3y e to the 3xy plus 21x squared over 2 minus 3x e to the 3xy. But recall, our original problem was e to the 3xy plus 7x to the third minus 2y is equal to 5. Now we can solve this for e to the 3xy. So I'll take these two over to the right side. And we got e to the 3xy is equal to 5 minus 7x to the third plus 2y. So we can replace the e to the 3xy's with 5 minus 7x to the third minus, oh, I'm looking at the wrong line, plus. Let me try that again. There it is. With 5 minus 7x to the third plus 2y. Okay, so we just solved this for e to the 3xy. We found out it's equal to this. So we're going to take our problem right here now, and everywhere we have an e to the 3xy, we'll replace it with this right here. So we're going to have 3y times 5 minus 7x to the third plus 2y plus 21x squared over 2 minus 3x, and I'm replacing this e to the 3xy with this. So we got 5 minus 7x to the third plus 2y. Now they might get rid of parentheses, I don't know. 3y times 5 is 15y. 3y times negative 7x to the third gives us negative 21x to the third y. 3y times 2y gives us 6y squared plus 21x squared over 2 negative 3x times 5 is negative 15x Negative 3x times negative 7x to the third gives us positive 21x to the fourth. Negative 3x times 2y gives us negative 6xy. And let me check that. 15y minus 21x to the fourth, or wait a minute, x to the third y, plus 6y squared plus 21x squared. And then 2 minus 15x plus 21x to the fourth minus 6xy. And that's our answer. A lot of books will do that. You know, here at the end, they'll plug in they'll solve this for e to the xy. The reason why is this is now all in terms of x's and y's. There's no e to a power. So if you can get rid of that, that e to the power is kind of a complexity in your problem you don't necessarily need. Now some books will stop right up here. So they'll leave this as their answer. It's hard to say for your particular textbook which one they might do, because I may be reusing this video for other textbooks, so they may do different items. But anyway, let me save that. There we go. And let's look at our next problem. I'll grab a drink too before I begin this one. Okay. Number 9. We have f of x is equal to 5 plus 3x, then e to the negative 4x. And we want to find the second derivative. Well, this is a product rule, so this will be my p, and this will be my q. Derivative of 5 plus 3x is 3. The derivative of e to the negative 4x is e to the negative 4x times the derivative of the exponent. So we'll take times the derivative of the negative 4x. That gives us e to the negative 4x times the derivative of negative 4x is negative 4, which then gives us negative 4e to the negative 4x for q prime. Okay, so then we'll have p prime q plus p q prime, our product rule. So for our first derivative, p prime was 3 times q, which is e to the negative 4x, plus p, which is 5 plus 3x, times q prime, which is negative 4e to the negative 4x. Now let me double check everything there. P prime times q plus p times q prime. Okay, we want to factor out what they have in common, and looks like they both have an e to the negative 4x. Now here that's gone, so that leaves us a 3. Over here we got plus 5 plus 3x, and this e to the negative 4x is gone, leaves us a negative 4 there, which gives us e to the negative 4x times 3, and then take this negative 4 and multiply it through the distributive property. Negative 4 times 5 is negative 20. Negative 4 times 3x is negative 12x, which gives us e to the negative 4x, and then we got negative 12x, and 3 minus 20 is negative 17. So we had to do a basic math error. Now I notice that these start with a negative, so I'll factor out a negative. So we got negative e to the negative 4x, and then 12x plus 17. Let me double check that. I'm kind of trying to double check myself so I don't put any errors in there anywhere. Q prime. Okay, that looks right. And factor that out, and that gives us 3 plus that. Okay, and negative 20 minus 12. Okay, that looks good. Well, that's our first derivative. So we need to do it again. This will be our P, and this will be our Q. Well, P prime, the derivative of the negative just stays out in front. The derivative of e to the negative 4x is e to the negative 4x times the derivative of the exponent. So we're taking it times the derivative of the negative 4x. Well, the derivative of negative 4x is negative 4, and I put it out in front, so I got negative 4 e to the negative 4x, which gives us 4 e to the negative 4x. That's P prime. Now Q prime, the derivative of 12x plus 17 is 12. So our our product, P prime Q plus P Q prime. For our second derivative, P prime was 4e to the negative 4x times Q, which was 12x plus 17, plus P, which is negative e to the negative 4x times Q prime, which was 12. Okay. Double check that. P prime, okay, times Q, okay, plus P, okay, times Q prime. Okay, that looks okay. Let's factor out what they have in common. 4 and 12, both divisible by 4, so I'm going to bring a 4 out. I'll bring out an e to the negative 4x, and let's see what's left. 4 is gone, that's gone, so we've got 12x plus 17. The e to the negative 4x is gone. 12 divided by 4 is 3 with a negative, so minus 3. Let me double check that. That's gone. Negative carries down. 12 divided by 4 is 3. So that gives us 4e to the negative 4x. 12x, 17 minus 3 gives us 14. And they're all divisible by 2, so I can bring a 2 out. I'll bring a clear out in front. E to the negative 4x. And when I factor out a 2 here, that leaves us 6x plus 7, which gives us 8e to the negative 4x times 6x plus 7. And that's our answer. So let me save that. And there we go. And let's look at our next problem. Now this says analyze and sketch a graph of the function, labeling relative extrema, points of inflection, asymptotes. We're going to kind of find everything on this. They're not asking for everything, but I just want you to see the thought process going behind it. If you remember that section on sketching graphs where we found all the different pieces, that's what they're referring to here. Our first piece, the domain. Well, if I were to rewrite this, this would be f of x is equal to x to the third over e to the not negative x, e to the x. That negative exponent, we can move it down to the denominator. Now I know we don't know if it's positive or negative, but this kind of indicates to you that we have a fraction, and where it's undefined is when the bottom part's equal to 0. Well, unfortunately, if I take a natural log of both sides, this is an exponential equation. And first part is get the variable in the part of the variable in the exponent by itself, no numbers in front of it, no numbers after it, and that's done. And then step 2 is take natural log of both sides. But natural log of 0 doesn't exist, so that doesn't go anywhere. So our domain is negative infinity to positive infinity. You can plug anything in. Now our x-intercepts. You always plug 0 into the other variable, so I'll plug 0 in for y. So we got 0 is equal to x to the third e to the negative x. Now, we learned in college algebra the zero factor property, where you got 0 on one side and you factor the other side. But they don't have to be nice binomials or anything like that. You can have anything factored. This times this. So we'll set the x to the third equals 0 and the e to the negative x equal to 0. Now here, this just gives us x equals 0. On this one, if I were to take natural log of both sides to solve it, again, I'm going to have natural log of 0, so that one doesn't go anywhere. So this is our x-intercept. And let me write this down. X-intercept equals 0. Okay. Now our y-intercept. We always plug 0 into the other variable. So plug 0 in for x. So I got 0 to the third, e to the negative 0. Well, 0 to the third is 0, and negative 0 is 0, and e to the 0 is 1. So 0 times 1 is 0. Which is no surprise. If our x-intercept is 0, then our y-intercept has to be 0 too, because that's the origin. And let me write down the problem here. Y is equal to x to the third, e to the negative x. Let me go ahead and put that on y1. So press y equals, press clear. And I got x caret 3. E, so I do second natural log, or second ln. And then I put in negative x. And closing parentheses. Okay. Now our vertical asymptotes. If I were to graph this, you see I have what that looks like that there. It's kind of misleading. Looks like it's just stopping there. It's not. I wonder if I can do a zoom to see a little bit better. Zoom out. 3 enter. Not too good. It's slowly inching out is what it's doing. I'll do zoom and 6 for Z standard, set it back. It looks like it's got an asymptote there. But we said our domain is negative infinity to positive infinity. There's no places where it's undefined. We can plug any value in here for x. So I know there is no vertical asymptotes, even though the graph looks like it. Now our horizontal asymptote. Well, you can look at the graph and kind of see it looks like it's leveling off there as it goes this way. Well, we can't use algebra to do this, but we could use our limit to study x as it goes to infinity. And that's of x to the third e to the negative x. Unfortunately, you don't know enough in business calculus with calculus techniques to actually find this limit. So for them to ask you about asymptotes is probably a little bit wrong. But anyway, I can take the e to the negative x, move it downstairs, becomes e to the positive x. Now if I were to plug infinity in, I'd have infinity third power, which is infinity, and I'd have e to infinity, which is infinity. So you have infinity over infinity. Now if we were taking Calc 2, there's something called L'Hopital's rule. And there's a lot of different things it says. But the main one with what we're going to be doing is that if you plug in your infinity and you get infinity over infinity, then L'Hopital's rule says you can take derivative to the top, derivative to the bottom. Which means this would become 3x squared. and the derivative of e to the x is e to the x. Well, now if I plug in infinity again, I get infinity over infinity, so I can take derivative again. So that gives us 6x over e to the x. And if I plug in infinity again, I get infinity over infinity, which I take derivative again, and I get 6 over e to the x. Well, now if I plug in the infinity, I'm going to get 6 over e to the infinity, which is 6 over infinity, which is 0. Like I say, you have to know more than what you know to actually find the asymptotes on this. So it's kind of misleading for them to actually ask you. But we know an horizontal asymptote is y is equal to 0 from finding the limit. And it kind of looks like it. Kind of looks like it goes up and then skims it. Now let me write some of these down. Okay. Horizontal asymptote is y is equal to 0. Now our slant asymptote. There is none. You'll have horizontal asymptotes on these exponential functions. But other than that, they pretty well exist everywhere. You know, I can plug in any x value here. I can plug in negative 50. Give me something different than what I might expect. It's way down, but well, now we're ready for our first derivative. So let me save that page. So we can tell increasing, decreasing, mins and maxes, and so forth. And let me grab a drink before I start that one. What problem are we on? Still on 10. Okay, so 10 continued. I think we're ready for step 7, increasing, decreasing. So our derivative, or our function, is y is equal to x to the third e to the negative x. Now we're going to use product rule. This will be p and this will be q. P prime will be 3x squared. Q prime, the derivative of e to the negative x is e to the negative x times the derivative of the exponent. Well, the derivative of negative x is negative 1, so I'll put the negative out in front. Negative e to the negative x. So for our first derivative, p prime is 3x squared times q, which is e to the negative x, plus p, which was x to the third, times q prime, which was negative e to the negative x. Now let me double check that. P prime times q plus p times q prime. That looks right. Now I can factor out what they have in common. Looks like they have an x squared and they have an e to the negative x in common. Now the x squared's gone, that e to the negative x is gone, so we've got 3 here. Minus that e to the negative x is gone. 2 of these x's are gone, so we've got 1 x left. Now, in terms of our second derivative, this is the one we might actually want to work with. That might be easiest. I'm just guessing. So let me write that down. Y prime is 3x squared e to the negative x. I'll put the minus out in front, so minus x to the third e to the negative x. Okay, now this right here, the reason why I factored it is to do increasing and decreasing, you have to find your critical values. So you'll set the first derivative equal to 0, and you'll solve it. Well, that means I set the x squared equal to 0, I'll set the e to the negative x equals 0, and the 3 minus x equal to 0. Now this gives us x equals 0, and this one gives us x equals 3. Now here, to get the variable out of the exponent, again I'll take natural log of both sides, but natural log of 0 you can't have, so that's going to drop away. So those are our two critical values. Okay, now our derivative up here. We want to pick test cases. And clear over here is negative infinity. Clear over here is positive infinity. So I want to choose something between negative infinity and 0, like negative 1. Something between 0 and 3, like 1. And something between 3 and positive infinity, like 4. Then we want to plug that into our first derivative. Now all we care about is a sign. So we got x squared e to the negative x and 3 minus x. Now the e to the negative x, that's like 1 over e to the x. Actually, I don't even need to think of it that way, but basically whatever I put into it, it's always going to be positive. Think about what I just said. Okay, if I put in 3 there for x, you'd have e to the third, 2.7 to the third power is positive. If I put in negative 2, negative is positive 2, so you'd have e squared. You'd have 2.7 in a bunch of decimal places squared, which is positive. Now x squared is always positive, so the only thing I need to worry about is this 3 minus x. So the first one's positive, that one's positive, and this one would be 3 minus a negative 1. 3 plus 1, which is positive, so this is increasing. Now again, this first one's positive, second one's positive, and we'll plug it into 3 minus x. So I got 3 minus 1. 3 minus 1 is positive, so this is positive. It's increasing. For the 4, first two are positive. Then I got 3 minus x, so I got 3 minus 4, which is negative, so it's decreasing. Now, if you want to actually plug in the values for all those, you'll find out that's what you come up with sign-wise. Because again, we don't care what the value is. All we care about is whether it's positive or negative. Okay, so this is increasing from negative infinity to 0. Then it's increasing from 0 to 3. And then it's decreasing from 3 to infinity. Let me write this down. Increasing from negative infinity to 0, and increasing from 0 to 3, and decreasing from 3 to infinity. Okay, now we need to identify, this is step 8, our relative extrema. Well, our extrema, our relative min, relative max, occurs when the increasing, decreasing changes. Well, this is both increasing, so that doesn't change. Here, this is increasing, and then it's decreasing. So assuming this point exists in my original function, this is a relative max. So we're going to have a relative max at 3, and then we need to find out what the y part is. So we're going to take that and plug that back into our original function. Well, we got x is equal to 3. Our original function was f of x is equal to x to the third e to the negative x. So we got 3 to the third e to the negative 3. Which gives us 27 e to the negative 3, 27 over e to the third. Now that doesn't help us a whole lot. So let's plug that in our calculator. See what in the world that value is. So 27 divided by e to the third. So second ln, third, enter. 1.3. So this is roughly 1.3. So let me jot that down. Remember, if you're going to sketch this, then it's nice to have that information in decimal form. That's our relative max. And let me save that. And let's continue with it. And I wrote down my first derivative here somewhere. There it is. Okay, let's look at concavity and points of inflection. So I got 3x squared e to the negative x minus x to the third e to the negative x. It's probably best when you find a derivative of these to have the e to the negative separate from the rest. So I'll factor out an e to the negative x. And that gives us 3x squared minus x to the third. And this will be p, and this will be q. So p prime, the derivative of e to the negative x is e to the negative x times the derivative of the exponent. The derivative of negative x is negative 1 times e to the negative x gives us negative e to the negative x. Now q prime, the derivative of 3x squared minus x to the third is 6x minus 3x squared. So p prime q plus p q prime So for a second derivative, p prime is negative e to the negative x times q, which was 3x squared minus x to the third, plus p, which was e to the negative x times q prime, which is 6x minus 3x squared. Now let me double check this. P prime, negative e to the negative x, times q, 3x squared minus x to the third, plus p, which was e to the negative x, times q prime, which is, okay. We'll factor out what they have in common. They both have an e to the negative x, so I can factor that out. And we're going to be left with, this is gone, we got a negative, so that negative is going to flip the sign of everything inside the parentheses. So we got negative 3x squared plus x to the third. And here we got 6x minus 3x squared. So that gives us e to the negative x. And we got x to the third minus 3x squared minus 6x squared plus 6x. Well, they all have an x in common, so I can factor that out. So we got x e to the negative x squared minus 6x plus 6. And that looks like about as much as I can simplify that. So we want to find our critical values. So I'm going to set the x equal to 0. I'll set the e to the negative x equal to 0. And I'll set x squared minus 6x plus 6 equal to 0. Now, the x equals 0, can't go any further with that. But the e to the negative x equals 0. I could take natural log of both sides, but natural log of 0 doesn't exist, so we can cross that out. Now here, I could use the intersect method on the calculator if I wanted to, or I could use quadratic formula. I'll use quadratic formula, just do something different. So a is 1, b is negative 6, and c is positive 6. So quadratic formula is negative b plus or minus square root of b squared minus 4ac all over 2a. And let me jot down the second derivative while I'm at it. So that's x e to the negative x squared minus 6x plus 6. There we go. So we're going to have negative b, negative 6, plus or minus b squared, so negative 6 squared minus 4 times a times c, all over 2a, which gives us 6 plus or minus 36 minus 4 times a times c, that gives us 24 over 2, which gives us 6 plus or minus square root of 12 over 2, which gives us 6 plus or minus, I can factor a 2 out, or bring a 2 out I should say, because 12 is 2 times 2 times 3, so we're looking for a pair of numbers, so a pair of 2's can come out. And since these three numbers are divisible by 2, this becomes 3 plus or minus square root of 3. Now remember, one of our critical values was x equals 0. And let's see what these give us. 3 plus square root of 3. And 3 minus the square root of 3. So we got 4.7 and 1.3. Okay, so we got 0, we got 1.3, and we got 4.7. Let me save this, and we'll go to a new page. Continuing with 10. It's assuming I haven't made a basic math error somewhere. That's my biggest fear. Especially at almost 1 o'clock at night. Okay. X equals 1.3. X equals 4.7. And infinity. And here's negative infinity. Okay, we want to pick our test cases. Well, if I plug in negative 1, something between 0 and 1.3 like 1, something between 1.3 and 4.7 like 2, and something over here like 5. Now keep in mind what these values are. This one is 3 minus square root of 3, and this one was our 3 plus square root of 3. Okay, now I want to plug these in my second derivative. I guess I wrote down my second derivative. It was x e to the negative x and x squared minus 6x plus 6. Now the e to the negative x is always positive, so I don't need to worry about it. But this x, if I plug in negative 1 there, that's negative. If I plug in negative 1 here, negative 1 squared is 1. Negative 6 times negative 1 is a positive 6, so that becomes positive. So this is negative, so it's concave down. That kind of makes sense when you look at the graph, doesn't it? Concave down. Then, at 0, we got x e to the negative x squared minus 6x plus 6. Well, if I put 1 here, it's positive. That's a positive. 1 here. 1 minus 6 is negative 5 plus 6. That's positive. Positive, positive is positive. So it's concave up. And then if I plug in 2 into my second derivative. So we got 2, which is positive. Now e to the negative x is positive, so I don't have to worry about it. 2 squared is 4. Minus 6 times 2 is 12. 4 minus 12 is negative 8. Plus 6 is negative. So that's negative, so that's concave down. Then if I plug in 5. X e to the negative x. X squared minus 6x plus 6. 5 is positive, so that one's positive. This one, 5 squared is 25. Minus 6 times 5 is 30 plus 6. 25 minus 30 is negative 5 plus 6 is positive. So positive times positive is positive. This is concave up. Okay, so for concavity, it's concave down from negative infinity to 0. Concave up from 0 to, and I'll put down the approximate instead of the exact value. So 1.3. When you're graphing, the decimal is better to have. And then it's concave down from 1.3 to 4.7. And then it's concave up from 4.7 to positive infinity. Concave down. Okay, and that 0 becomes concave up. That looks correct. And then concave down from 1.3 on. There, that looks correct. I hit over here, somewhere at 4.7, and it becomes concave up. So that seems to fit. Never hurts to actually look at your graph as you find these to see if they match. Now our points of inflection. Our points of inflection exist when the concavity changes, assuming the graph exists there. Well, here it changes from concave down to concave up, so at 0. Here it changes, so at 1.3. And here it changes at 4.7. Well, let's plug those into our original function and see what we get. Now, I'm not going to get exact values. I already have this original function on my y1. Now, you have to make sure you're in the correct mode for your table. So if you do second window, you want your independent to be ask. So if it isn't, down arrow to independent, right arrow, put your flashing cursor on the ask and press enter one time. Then second mode, exit out. Now if we go into second graph, and you may or may not have numbers there, I'll delete those, get them out. We got 0, enter, 1.3, enter, and 4.7. Enter. So we're going to have 0, 0, 1.3 and 0.6, 4.7 and 0.9, like that. Those are our POIs. And let me jot those down. 0, 0, 1.3, 0.6, and 4.7, 0.9. Okay, let me save this. And we're ready to do our graph now. Actually, I might have room down here. Let me see, what do I got? I got my x-intercept, y-intercept is 0. Relative max is at 3, 1.3. So 3, 1.3, maybe right there. That's gonna be my max. Our POIs, one's at 0, 0. So this is I'll label it, well, POI. And the next one is 1.36. So 1.3, or 0.6, sorry. That'd be a POI. 4.7. 1, 2, 3, 4, 5. 4.7 and 0.9. So that'd be a POI. Okay. And it's increasing from negative infinity to 0, so it's increasing here. Now here I don't know what kind of angle it's coming out of. I do because I've looked at the graph, but I would have to plot some points to see this. And it's concave down initially, so it's coming up there, hitting that, and then the concavity change. I didn't write this down, unfortunately, but if you like, it's concave. Remember, the POI is where the concavity changes. So this is concave down, so then it's concave up, like that, and then it's concave down, like that, and then it reaches this, and it's concave. Anyway, you get the idea. And then it's a horizontal asymptote there, so it's skimming that. And that'd be our graph. As close as I'm going to get. But again, this is what it really looks like. Now this, I don't know why I graph those kind of weird. Let me see if I can do it without erasing the entire line. Probably not. Draw my axis straight. There I go. Okay, then this one skims that. Getting real close to it, but never touches, never crosses. That's better. I like that. So let me save that. And it's always comforting when you solve your problem and your answers you come up with actually make sense. You know, concavity, POIs, you know, especially when you can see the real graph. Now, the last thing we're going to be talking about is equality of exponents, which is this problem here. So let me write that down. Our equality of exponents says if you got b to the p is equal to b to the q, then you can set p equal to q. Now, typically, b's are like numbers. Like you got 2 to the power equal 2 to the power. 5 to the power equals 5 to the power. If you got that, then you just set the exponents equal to each other. Let's look at number 11 here. We've got e to the 4x minus 1 equals e to the second power. Well, they're both e to a power. So for my equality of exponents, we can just set the exponents equal to each other. So we've got 4x minus 1 equals 2. And then we'll solve for x. So I'll take negative 1 over, becomes a positive 1. We've got 4x is equal to 3, or x is equal to 3/4. I think that's our last problem. So let me save this. And then I'll stop the recorder.